So now we will see the third one, that is the bistable multivibrators. It also has two states. Both states are stable. So we will see this bistable multivibrator using these subtopics: definition and design components, circuit construction is my circuit construction and working principle, output waveforms, formulas and applications. So here also we have the same basic building blocks. We have the amplifier 1 stage, amplifier 2 stage. This is a transistor 1, transistor 2, and we have the coupling network in between. This coupling network is made by resistors and capacitors. Okay, so and also these A1 and A2, they provide the required phase shift, that is the 360 degree, 180 plus 180. And here we can, this A1 and A2 can be either transistors or operational amplifier or 555 IC, the same. So today, of course, in our lecture, we will use the NPN transistors in instead of A1 and A2. The goal is generating non-sinusoidal waveforms. That is the function of multivibrators. Remember, bistable multivibrator. In bistable multivibrator, it's also a two-stage amplifier with two states. So we have two amplifiers and it produces two states, that is a logic high or logic low, or logic high and logic low. So here both states are stable. So if you want, for example, if it has 0, it's stable. Whenever you give the trigger signal, then only it will change to another state. And then it will maintain this state logic 1 forever unless you give another trigger pulse. If you give another trigger pulse, then this will come to logic 0. And then it will be staying in this logic 0 forever until you give another trigger pulse. So both states 0 and 1, both states are stable. If you want to change the output status from 0 to 1, you must give a trigger pulse. Similarly, if you want to change from 1 to 0, you must give a trigger pulse. So that's why I mentioned here, it continues in a specific state, either 0 or 1. Whenever we give trigger pulse here, it changes from one state to another state. So both are bistable. That's why we call this a bistable multivibrator. So this is the circuit design of bistable multivibrator. So as I said, whenever we look at the circuit, we have to look from circuit construction perspective at first. So here we connected two transistors back to back, Q1 and Q2. And even though they are identical, they use different doping levels to turn on the transistors at different timing. So it means when Q1 is on, Q2 is off, that one is changing based on the way you connected. Okay, so this story you already know that. Now we will see a little more detail. So here we have the RL1 and RL2, two low value resistors which are connected in the collectors of Q1 and Q2. It helps to keep the collector current in permissible stage or permissible range. It means collectors you can control. Where is the cursor? So this is the collector, right? So we have two collectors. So we can control the current flow in the collectors by using these RL1 and RL2. So we call this as a permissible range. So we can maintain the permissible range current flow in these collectors by using these two resistors. This is also, we can call this as this is helping us to have the biasing or biasing stability. So now you can see another connection. So here the collector, okay, this is the collector and this is the base and this is the emitter. So the collector of Q1 is connected to the base of Q2 via R1 and C1 parallel network. So here you can see collector of Q1, that is node A, this is the node A, is connected to the base of Q2 via parallel R1 C1 network. Parallel R1 C1 network. Similarly, collector of Q2, this is the collector of Q2, this is the collector C, and this is the base, and this is the emitter. So collector of Q2 B, node B, is connected to the base of Q1 via this C2 R2 or R2 C2 parallel network. Okay, so this is the second point, and then the third point. Now, same principle. We apply the supply voltage. We assume Q1 is equal to on and Q2 is equal to off. So Q1 is on and Q2 is off. So maybe we can make some kind of a small table. The step 1. So let us say Q1, and the output of a Q1 is A, node A, that is the collector, and then the transistor Q2, and then the output of Q2 is node B, that is the collector of Q2. It's connected like this. This is the step 1. We will see what is happening in the step 1. The step 1, Q1 is what we are assuming here. Q1 is on and Q2 is off. Q1 is on, Q2 is off. So we know what will happen. Once the Q1 is on, there is a short circuited, the voltage potential will go to 0. So this will become logic 0. So immediately the node A will become 0. This node A, 0, will drive the base of this transistor. So the 0 voltage cannot turn on the Q2. So the Q2, it will maintain off state. So it will be in off state. Because of the off state, this is open circuited. So the voltage will be accumulated at this node B from this VCC. So this will become logic high. So this will be logic 1. This is step 1. So this is the stable state. So at node, it will maintain 0. At node B, at node A, it will maintain 0. At node B, it will maintain 1. So now I am applying the trigger signal. You see here, the base of the Q1 is connected to trigger signal. Base of Q2 is also connected to the trigger signal. So now we will see. Now if I apply a trigger to the base of Q2 via C4. So this is the base of Q2. I apply the trigger here via C2. I already told this C2 is the blocking capacitor or coupling capacitor. So now I am applying this large amplitude, short duration trigger to the base. Then what will happen? Then this transistor will immediately go to on. So now this Q2 will go to on. If the Q2 goes to on, then this is short circuit. Then this voltage potential will go to 0. Then this will become logic 0. The voltage potential at this node will become 0. So let us go back. I write at node B, the voltage is 0. So because of this voltage 0, this will drive the base of Q1. So this 0 volt will maintain the off condition in Q1. So this will maintain off condition in Q1. So because of the off condition, this is the open circuit. So the voltage will accumulate at this node from the VCC. So this will become logic high at node A. logic high at node A. This is a step 2. Remember, I moved from step 1 to step 2 by applying the trigger signal. This is very important, you should note down. So here I applied the trigger signal, then only I moved to the step 2. I am changing from one state to another state. So this is maintaining, this will maintain this 1 and 0 in node A and B forever. If I want to change now, I have to apply the trigger signal again. Let's say here now. So this is the second stable state that we know that node B is 1 and node A is 0. And node B, so this is 0 and this is 1. 0, 1, and then the 1, 0. A is 1. And so now if I apply the trigger again to the base of Q1, is the cursor, yeah. Now if I apply the trigger to base of Q1 via C3, so here, now I apply this trigger signal to the base of Q1. Then what will happen here? The Q1 will be on immediately. So if it's on, then there will be a short circuit. So the voltage potential will go to 0. This will become 0 volt. And this 0 will go down and drive the base of this one. So now the node A will be 0. Let me go back. Node A will be 0 because Q1 is on. This 0 will drive the base of this one. Then this will be off condition. So this open circuit. So the voltage will accumulate. So this node B will become 1. So Q2 is off. Because of that, the collector voltage will increase and this will be 1. It's because this is the state from S1, the step 1, step 2, this is step 3. We are changing from step 2 to step 3 by applying this trigger signal. So the output will be maintained at these nodes forever until you apply the trigger signal. So once you apply the trigger signal, then you are changing the status. So if it's, for example, at the first, if it's 0 and here is the output 1, then I apply the trigger signal, then this will become 1 and this will become 0. And again, I apply the trigger signal, then this will become 1 and this will become 0. So you can easily apply this one and see the circuit operation, how it works. This is how we are using. This is the operation or the working principle of bistable multivibrator. So the output is just stable, either in 0 or 1. If you want to change that, you must apply the trigger signal, external trigger signal. So until you apply the external trigger signal, until you apply the external trigger signal, the output will be maintained in the same state. It will not jump back by itself. So here it is. Here you can see this is the circuit. So this is the switch position. So it means this is the trigger signal. So I apply the first trigger, that is the input 1. So then what will happen? So V01 at node A is high here. So normally this at node A, this is high. And then V01, V02 at node B, we just take like this column, the first column. So V02 at node B is low. This is this low. Low means 0. And this high means high. That is the initial condition. So now I am applying the trigger signal. After I apply the trigger signal, then immediately this logic, right? This is the V01 at node A. It will become logic 0 because I am applying the trigger signal. And this is the second trigger. And the second trigger, now immediately this one will become 0 and this one will become 1. So if you look at this one, whenever you apply this trigger pulse, then the output is changing. So if the node A, this is the node B. If the node A is high, the node B is 0. If the node A is 0, then the node B is high. It's like that. So we are controlling the output status by applying the trigger signal. So alternatively, you are applying the trigger signal and changing the on condition and off condition. Accordingly, the output will change. So here you can see I just explained the graph here in this text that you can read that. So here RL1 and RL2 must be selected. There are some conditions in this bistable multivibrator. This RL1 and RL2, you have to select in a way that can control the collector currents, and also the VBB and the R1, R2, R3, R4, R1, R2, R3, R4. These values must be the correct value in order to keep the Q1 and Q2 either in off condition or on condition. On condition means that you are driving the transistor in the saturation region. Off condition means you are driving the transistor in the cutoff region. What is the saturation region, cutoff region? I think you should know this. Saturation means the transistor is on. You are making a short circuit. It means you already melt the depletion layer. No more depletion layer. So you are making the conduction between emitter and collector. Cutoff region means, so here the transistor is on. Cutoff region means here the depletion layer width is quite high. So you are making the E emitter and collector as an open circuit. So there is no connection. This is a disconnected. So this is the off condition of the transistor. Okay, so in order to maintain this one, you must select the correct values of the resistors and capacitors in the RC network. So yeah, the same, when the base current is high, it should drive the corresponding transistor in saturation region. So it should be very sensitive. So whenever the base voltage, the VB, if it goes less than the threshold voltage, VT, immediately the transistors should go to the cutoff region, off condition. But whenever the VB, base voltage, goes greater than the threshold voltage, immediately it should drive the transistor into the saturation region. So there should be a conduction between emitter and collector. So you have to choose the correct RNC values. Remember, bistable circuits are not self-triggered. In astable, it's a self-triggered, but in bistable, this is not self-triggered, as they rely only on the user provided trigger inputs to change their state. So I am externally applying the trigger signal to change the status. In these circuits, the output waveforms obtained at node A and node B are complementary to each other. So of course, whenever you have the logic 1 here, you will have the logic 0 at the node B. So if you change this to 0, and then this will automatically be 1. So that is the nature of the circuit. Okay, so that is why we call this as a complementary. So if this is 0, the complement of 0 is 1. Or if this is 1, then this will be 0. So now we will see the applications. Applications of this bistable multivibrator. It's used as flip-flops in digital operation, in computers, and also we are using this bistable multivibrator in some digital communications. We can also use this bistable multivibrator as a toggling switch. Toggle back and forth, but the toggling is only happening when you press the switch. When you press the switch, it will change the status. For example, you press this one, the LED is on. If you press the button again, the LED goes to off. And also we can use this bistable multivibrator for counting and storing binary information. Storing binary information, we are talking about flip-flops. That is the purpose of flip-flops. Flip-flops are used to store the data either temporarily or permanently according to the configuration where you are using. So it's storing the single bit data, either 0 or 1. So we are using the binary information. We are storing the binary information using flip-flops. Flip-flops can be made by this bistable multivibrator. You can also use this one in frequency divider of timing circuits, and also we can use this to generate clock pulses and clock pulses for relay controllers. So bistable multivibrators are also used in so many different applications. So really depending upon where you are going to use, you have to select the correct multivibrator, either astable or monostable or bistable multivibrator. Please try to go through oscillators and multivibrators lectures, and this is easy to understand when you look at freshly instead of after some time.